Good morning. Just setting up a few more things. Let me know if you can hear me well. About half the class is here. I'm sorry I sent the notices late, but I really want you to learn to find it in the playlist. I don't want you to depend on my sending the link, all right? I want you to find the stream in the playlist because every day sending the link is unnecessary. So just keep in mind, if you see a blurry screen, be sure to refresh. So are there any questions about the Moodle page, about the videos I asked you to watch so far, about anything regarding the course? Some people asked me or sent me emails about the textbook. You can work with my notes pretty much, but I did provide a text for reference, and there is a Spanish version of the text in an earlier edition. Okay, so what we're going to do today, the plan is to finish Unit 1 and then start Unit 2. For Unit 2, the first part, you need your calculator, and I asked you to make sure you have one every class. And remember, I asked for the TI BA2 Plus because that handles two variable statistics. It makes this course very easy. Well, more seamless, let's say. If you have other calculators, you need to learn how to use it. And I mentioned in the prontuario what the requirements are for the calculator. So you need a calculator. I'll also show some things in Excel, but I prefer for you to have a calculator. Most times, to build that confidence with statistics, I like to build independence, right? And I just feel you're more independent if you have a calculator, even if it's just a calculator on a smartphone. That builds independence rather than having to start up your computer, turn on Excel, and Excel is a little more bulky compared to pulling out your phone and conducting calculations, okay? All right, so we're going to pick up the discussion on experiments. So we left off here. We had just talked about the good types of experiments or the ideas behind experimentation and having realism in experiments and so on. And we want to talk about lurking variables now. There was an example presented in the decision through data videos to explain lurking variable. There were a few actually. And one was one example that was used was this one. it's been observed that when ice cream sales are high, the number of drownings on the beach are also high. Does that mean that eating ice cream causes people to drown? Is that a causal link? And they suggest no, it's likely not. Rather, this is an association, not a causation or not a causal relationship. In fact, this probably can be explained. The fact that this variable goes up, so ice cream sales, you can think in dollars, and drownings goes up because of their relationship to a third variable. And they propose beach population which may be because of the temperature on the beach, or maybe I'll write them side by side. Is that how I do it? Let's do that. So maybe it's the relationship, if I use the arrows to mean causation, the temperature on the beach or outside so the temperature outside, the ambient temperature, brings people to the beach, right? People want to be out on the beach when it's hot. And so the hotter it is, they're going to be on the beach. So there's going to be more people on the beach. So there's more ice cream sales and more drownings. That's probably what's causing this one to go up and this one to go up at the same time. Okay, so if there's any kind of causal effect, it's behind what's going on here. So what about this? If in this case, we were able to identify a source, right? We could say, well, temperature seems to be associated with the beach population, and the beach population contributes to more drownings and also to more sales. So we could actually get information on these variables. All of these variables, actually, we can get information, but I guess the goal would be to be proactive and try and reduce the fatalities from drownings or the injuries from drownings by ensuring that you have enough lifeguards or security on the beach to assist if somebody drowns. So what you might do is monitor the temperature and keep a record of the temperature and keep a record of the drownings and realize, recognize at a certain temperature. So let's take these two variables. Once a certain threshold is reached, the management will be notified to hire a lifeguard on standby, someone who can step in and help. So the idea that we could do that with temperature is obvious, but we could also do it with ice cream sales because it looks like there's some sort of relationship here. We could also be monitoring, let's say you're the manager of the beach, okay, so you're in charge, and you have hourly reports about ice cream sales, or every half hour You're informed by the ice cream salesman about, the ice cream sale. So you have information on that too. It's possible. It's possible. And maybe temperature is easier to monitor. All right. You don't depend on someone else. You can just look that up. And so in this story, if you actually monitor these two, this would act like we would say that temperature is your explanatory variable. And drownings are your response variable. Am I saying that the heat is causing people to drown? No, I'm identifying this link between temperature through beach population and drownings that can be monitored. Still, I'm not saying temperature causes people to drown. Okay, so this is an association I can use to reduce the fatalities or injuries from drowning. So what we say, until the point where we recognize temperature as the explanatory variable, or use it as the explanatory variable, or even we could have used beach population as the explanatory variable. I think this is easier to get, right? Until that point, and looking only at, let's say, ice cream sales and drownings, the explanation for why this is happening is behind what we're looking at. And until we recognize temperature or beach population as explanatory, we would call these lurking variables. So usually the term lurking variables is reserved. I'm trying to see, what color should I use? Lurking in the distance, or lurking behind. What you might otherwise see. Okay? So that's my explanation. So lurking variables are those that are not yet identified. Once they're identified and you can actually study them, they have a new name. They're called explanatory variables. So the term lurking variables is reserved for when you don't really know what it is. So let's say that there was the example in the video regarding the relationship between smoking cigarettes and cancer, and particularly deaths attributable to cancer and in human subjects. And the argument by the tobacco manufacturers was for a long time that you haven't conducted an experiment on humans to prove that smoking causes cancer, so you can't say it. And they propose maybe there are lurking variables behind that does two things. It both causes somebody to smoke, and it also predisposes somebody to cancer. So it's not necessarily a causal link between smoking cigarettes and cancer. So they created some confusion. So this was the proposed relationship. Cigarette smoke causes cancer or death due to cancer. And they said something else is behind, lurking. Right? There's something behind that could be explaining, causing causing people to both smoke cigarettes like a genetic factor that both increases the likelihood that someone smokes and increases the risk, how did I term it? A predisposition to developing cancer. That kills you. Okay, so that's how they got away with it for a while. So similar to the beach population and temperature sort of thing. So while they didn't identify what it was, they didn't find these factors to be a direct cause, whatever it was, the set of variables that could be lurking are called lurking variables. Any questions? Oops, I went way out. I just want to go back. And you can text me if you want to write me privately, you can text me as well. My number, I'll put it in the chat. What we could do is, if you wanted to speak, I could in a WhatsApp or in a different app, I can just have you guys in there, and when you're ready to speak, you let me know. I mean, it's another screen for me to watch, but if you really want to speak, we can do that. Let me know. But if you're fine with chatting, that works for me. All right. So I mentioned here in the notes that the use of rodents in experimental trials in place of human is obvious, right? It's safer, but it's still, on the other hand, it's still not a human. So what justifies using a rodent as though the results carry on to humans, or the findings carry to humans? It's because the rodents metabolize substances like humans do, and their biochemistry is like that of humans, so that we can draw inferences from findings and say, this is what would be the outcome in humans. Also, it happens quite quickly. The life of a rodent is shorter, so we'll be able to see the results. The lifetime of a rodent is a fraction of the lifetime of a human. So we can save lives. That's the idea. And unfortunately, the other side is that, they use rodents and not, they're not using dogs and cats for experiments, right? Because people have an affinity to domesticated pets. In fact, I think in Canada, they've outlawed any use of animals in cosmetic development. They haven't done it for drug developments yet, but for cosmetics, they've done it. In fact, I've mentioned in the last class, I believe, they actually genetically manufacture mice and rats, guinea pigs, for experiments, so that they're all to rule out any kind of systematic biases, right? So they have them all be the same, and then they introduce a treatment and they look at the effect, or they create a defect. They even manufacture them with a defect, and then they use treatments to see if there's any positive effect. And the idea of manufacturing labs for animals for experimentation, people won't feel so defensive towards rodents, unfortunately. Unfortunately, I'm not sure which it is. All right, so just a review of sampling before I get in a little deeper into the discussion of experiments. So examples of samples include the results or the data sets for opinion polls and labor market surveys and etc. Sampling is conducted when we want to measure certain characteristics in a population, the target population. For example, the proportion of people who favor the Democrats, the proportion of ball bearings on a circuit board, and the average disposable income in a region. It's often the case that we need to take a sample, even though a census would be ideal. It's hard and it's costly to sample everybody, and that was demonstrated in the videos I asked you to watch. And as a result, even trying to do it, you might not end up with a complete census anyway. So that will create bias. At any rate, it's easier to just focus on a smaller set and do it and collect it very well. So there's just some summary points about sampling. Sampling of subjects, it's not like in experiments. You don't do anything to the subjects that are sampled, whether they're human or otherwise. You don't interfere with them. You just collect data on them. If it's human, you ask them questions. Otherwise, you observe them and record your findings if it's a non-human subject. Samples are collected randomly, which does not mean haphazard. It means that it's done in a systematic way, in what we call a random fashion. Samples arise more frequently in social sciences than they would in the natural sciences, because we have the gold standard of experiments for the natural or pure sciences. We have to be careful in samples not to introduce bias. And then I just mentioned some examples in the video to help remind you what was in that video. So the census would be the attempt in the U.S. Census to actually count all the homeless. And examples of surveys, I just mentioned a couple to jog your memory. NRC and the U.S. Census Bureau surveys. That's it. Okay, questions so far? So I'm going to get into experiments, into the details of experiments now. This is something that wasn't addressed explicitly in the videos, so I'm going to take some time to formalize the terms. Okay, so in an experiment, there are identifiable features. Okay, so there's the experimental unit, which is the subject that's acted upon. There are the treatments, which are the conditions applied to the unit. So this is the intervention used. The response variables are clear, they're measurable. we refer to the explanatory variables broadly as factors. So there could be one, there could be many. And then each of those factors could have different levels. All right, and we'll get into that. So for example, let's talk about experiment 1, where we get an individual to consume 1 ounce of alcohol and measure the blood alcohol level after 1 hour. The experimental unit is the individual consuming the alcohol. The treatment is the actual action of ingesting the alcohol. The response is the measure of the blood alcohol level after 1 hour. And so there's only one factor, it's alcohol, and there's only one level, 1 ounce. We could vary the level by having it be 1 ounce, but introducing another variable that is percentage alcohol content. So we could have first level as vodka, but 1 ounce of vodka, or wine, which is 1 ounce, 1 ounce of wine, and these have varying percentage alcohol levels. So, questions? It was explained in the video that randomized comparative experiments work provided, and I'm going to add, that they have observed the 3 R's of experimental design. First, representation, actually identifying the effect of the treatment through control. Randomization, to ensure there's no systematic bias affecting or confounding your results. And replication, to rule out that it's just by chance that you're seeing the effect of the treatment. Our goal is to identify statistical significance of the treatment or treatments that we apply. All right, so to illustrate the first, let's talk about control. I'm going to illustrate experiment number 2 that I refer to as the gastric ulcer freezing experiment. So this experiment is conducted for people suffering from stomach ulcers. And if anybody's ever had ulcers or they've had intestinal or gastric ulcers, this is you're going to appreciate the need for relief. So the idea of a treatment was proposed such that a liquid solution could be administered to exactly precisely the spot of the gastric ulcer. It's a cooling solution that was developed, and the question was, is this actually going to have long-term benefit, or the medicinal qualities of this substance, is it really going to help reduce the pain experienced by the patient? So people were enrolled in this study, experiment 2, and they were surveyed at the outset. They met with, their doctors referred them to the experiment. They contacted the clinic where the study was being conducted by phone, and the patient was screened. And after they were invited for the treatment, they were given a survey to observe their pre-treatment self-reported level of pain. Then they were ushered into a room where the treatment was applied, and the treatment involves the nurse, the clinic staff, administering through a tube. First, one moment, making me cough thinking about it. So at the throat, some spray anesthetic would be administered. The patient would open their mouth, they'd spray, and then some time would pass to make sure that the patient's throat was numb, and then a tube would be inserted down their throat, and using ultrasound, they'd locate the position of the ulcer, and then begin to release the treatment. Once the treatment was administered, the tube would be removed, and the patient would be put into another room where they would have some time to rest, recover, and then after some time, they would be administered the survey again, asked about their level of pain or discomfort, and some other exit questions. So in this experiment, the experimental unit is the patient with the ulcer. The treatment is a solution applied to the location of the ulcer to reduce the production of acid that causes the pain. The response is the self-reported level of pain. The factor is the solution, and the level of the factor is the temperature of the solution. And there's a medicinal property to the solution, but we're going to mark the level of the factor being the temperature. So what's wrong with this experiment? I use quotes, the so-called experiment. What's the problem? Is there a problem? Is there something missing? Right. So Herodotus points out there is no control group here. In experiments with human subjects, you must have a control group. So as I outlined the first class or the last class, what we need to do is have two groups, but otherwise treat them identical. However, the control group receives a placebo, something that looks exactly like the other treatment but doesn't have the same medicinal benefit, okay, or proposed medicinal benefit. So what's done is, let's say this is the control group. What we can do is we can measure the percentage of patients, for instance, or let's say the scale was 0 to 10 pain report. So the patients have to say 0 to 10. Okay? And then let's say we just calculate the average of the report. So let's say the control group ended up with an average of let's say 5. I have to do this before and after. Wait, I need to make more space. let me do this again. So if you have two groups that are otherwise, it should be many individuals, so that the group in the control and the group in the treatment on variables that could influence their self-report level of pain, which is the response, that these groups are otherwise identical. So you have just as many people in the control group as you do in the treatment group who feel, a moderate level of pain. And you have just as many people in the control group as the treatment group who experience a severe level of pain. And so then their characteristics that could lead to that is their diet, or their age, or their gender, or so all the variables. Because we've sampled enough people, or we've randomized enough people, the group characteristics between control and treatment are similar enough. Okay, that's the idea of creating these groups. So the only thing when I compare the results of their response, it should be similar. So before the test, I should see about the same level of pain in both groups. So let's say on average, it's about, let's say this is a 6. So the level of pain is a 6. Okay, so it works out, so it's like about the same. Let's say it's 6. So 6 is the average self-report level of pain. So the factors that we believe influence their level of pain are, roughly evened out. You know what I'll do is I'll put a decimal on that. So it's a little bit different. Okay, so then after the treatment, what happens? Well, if we just do if we conduct a single study, we don't get to look at it this way. I'm going to propose with the control group now, we should look out to see that the people with the treatment have a significantly improved self-reported level of pain. So what will happen is, because of the placebo effect, it could be that it affects both the control and treatment group, right? That just being part of the study, going through the trouble of finding calling the clinic, finding the clinic, undergoing this uncomfortable treatment, spending your day there, you have got to have a lot of hope that this is going to work, right? You've invested a lot in this. You did some research possibly before you engaged in this. You searched the internet about these trials, and you have a good sense that you're going to feel better. That optimism that optimism leads you to release in your body positive endorphins. Endorphins in the body are known to have biochemical effects that actually help a person or who in pain. It helps alleviate the pain. Okay, so it's like a painkiller, a natural painkiller. It's a feel-good chemical that runs through the body, or a set of chemicals. So this 8.2, even though these people in the control group didn't receive anything, they just went through the study, they're reporting 8.2 level of pain. Are they lying? No, they're not lying. They actually feel better because the whole process made them feel better. So that now puts weight and burden of proof on the treatment group that they have to exceed that 8.2 average. Now, you think that's easy? The placebo effect is also going to affect the treatment group, right? But we believe, the idea is we have to supersede the effect of the placebo effect that's been, the baseline for that has been captured in the figure 8.2. So yeah, it's the placebo effect. The Hawthorne effect that I mentioned is if the patient actually changes their behavior. So the Hawthorne effect could have been being part of the study, that a person engaged in the study before they showed up. Maybe they did all the right things that they've been told to avoid having the gastric ulcer pain. They had a plant-based diet, and they slept on time, and they reduced stress, and they did all these things. So that would be the Hawthorne effect. So I could write that in as well. Usually you hear about the placebo effect. Okay, so both of those. So you want to, this could have been caused, clearly this is caused by placebo and the Hawthorne effect because you didn't do anything to this person. You just engaged them in the study. Now, that's not to dismiss the effect of the placebo. Before it was deemed unethical for doctors to give patients placebo, patients were administered placebo pills, which were just cornstarch or sugar in a capsule. Nothing with a particular taste or distinction from other kinds of pills or tinctures. But all that it did was make a patient feel like they were addressed, their pain was addressed. You cannot underestimate the impact, a positive impact of someone being acknowledged for their pain. Someone having their pain acknowledged just feels better. And it's important to be able to do that. But we want to use science here, right? We want to be able to attribute the response to the actual treatment. So that's why we separate out by conducting a control trial. And once we do that, this has to do better than 8.2. Now, I'm just drawing, this is just a sketch. But the idea is at some point up here, we will attribute statistical significance. How far up? Well, by the end of the course, we'll talk about how to measure that. But it has to at least exceed this amount. Okay. Questions? So it turns out when the experiment was conducted with a control group, that I've made these up. I've invented these scenarios, but it's, in this case, what I say is once I introduce a control group, in fact, there is no difference found between the placebo or the control group and the treatment group to attribute positive or significant, statistically significant improvement due to the treatment. Questions? Did I make that too small? So again, take screenshots if I'm going too fast. Also, don't forget to refresh your screen if you see that the screen is blurry. All right. I need to add that in conducting the test, whether the patient is randomized. So the thing is, let me just say, behind this, the description, patients who were selected for the study or screened and admitted to the study, they were put on a list, they were numbered, like labeled, and then they were selected to be or assigned to the control group or the treatment group. Okay, so that assignment was done in advance, and then people were contacted to show up. And before they show up, their vials, the vials for the patients, are labeled, but the contents are not labeled, so that the nurse is administering the treatment that was prepared and with labels in the lab or the pharmacy of the clinic or the hospital or of the manufacturer of the product. That nurse doesn't know which vial is which. So that's really important. It's very important that the nurses, the staff treats the patients the same, right? Otherwise, what would happen? Well, they might want the patients who are really suffering to get the treatment, and this is not unheard of, this happens. They would want the patient to really get the treatment that will alleviate their pain, so that they'll flip, they'll give, if it was up to them, they'd give them the treatment, right? They wouldn't withhold the believed treatment. Remember, we haven't tested these yet, right? We're in the process of testing if these are actually effective. Actually, I got in an argument with a friend. I don't say it's an argument, it's just a Facebook chat, but she was insisting that people who ask for medication should get the medications they want, and I suggested, well, there's cost to everything, and there's cost constraints, and we got to use the ones that actually work, right? We shouldn't be using the ones the patients think they need. It should be the ones, obviously the patient themselves is biased about what they need and they want to alleviate their suffering. But there's a responsibility to determine the effectiveness of drugs, and it's unethical to give patients drugs that are not known to have any actual treatment effect. Okay. So I just outlined how would we tease apart the elements of experiment 2. Well, still the patient with the gastric ulcer is the experimental unit. The treatment will be the cold applied to the location of the ulcer to reduce the production of acid. The response will still be the self-reported level of pain. The factor continues to be the solution applied to the gastric ulcer. In the level, I'm going to separate now. So everything else was the same. What I'm going to do though is vary the temperature. I'm going to use the actual treatment for the treatment group, the cold temperature product or solution. But for the placebo group, I'm going to use a body temperature liquid like water for the control group. So I'm not going to have, the patient is not going to have that treatment. Everything else pretty much looks the same, but they're only going to have liquid body temperature water administered at the site. Okay? So in conclusion, I'm going to say the result for this experiment as described above was that there is no, the freezing has, the cold solution has no effect on the self-report level of pain. And in fact, in conclusion, it's just people hoping to get better that made them feel better. This is the placebo effect. And you can throw in that maybe they changed their behaviors and that helped too, but that's the Hawthorne effect. Comments or questions? All right, we're on to experiment number 3. So the first one was just to teach you the elements of an experiment, the components of a good experiment, or then the second experiment was the gastric freezing to introduce the importance of the control group. And now we are on experiment 3. Experiment 3 relates back to the video, and in particular, the physician health study, where I'm going to give you some details that were presented in the video. We're going to talk about them a little bit. Where 21,996 male physicians were tested to investigate the long-term effects of aspirin. In fact, doctors were treated with both aspirin and beta-carotene to answer 2 research questions. 1, does aspirin prevent heart attacks? And 2, does beta-carotene prevent cancer? So they took advantage of the fact that they had identified 21,996 male physicians willing to participate and thought, let's take advantage of this sample and administer both those treatments. In this case, there are actually 2 factors, okay? And when there's 2 factors, each factor must have a placebo. So that turns out like a factor study like this, where you have both factors, and then here both placebo. So some patients will be randomized into this group, some into this group, so with both treatments and one with neither treatment, and then either these groups. So how is this done? This is done by first recruiting participants, then labeling all of them. We're going to go through every step, and then assigning them to the treatment groups. There's actually 4 treatment groups here. But first, I want to ask you, why were male physicians used for this study? Why not females? Why not construction workers, or teachers, or engineers? Why was it male physicians? Okay, good answers. All right. So there's many reasons. First, male, because as much as people want to argue or suggest that women are the, women have gone through undue suffering, and the truth is that men die first, okay? And they're most likely to die of heart attack, okay? So men die first. Men die before women. So they're dying at a younger age than women. Women live longer. So, however you want to see that, in medicine and in economics, everything tallies up, with who survives and who dies. So whatever your lifestyle decisions, whatever your predisposition, whatever you've been endowed, you're not doing so great if you die first. So men die first. And so for one reason, we want to help men who die first. And we want to prevent that. So let's study men. For another, which is, I guess, more important for the study, because you want to be able to generalize. Remember, we talked about being able, or we're going to talk about being able to generalize the results, because this was studied on men. Can you really say that this carries to women? Well, the fact is, since men die first, we're more likely to see deaths of men for the purposes of the study. So each year, and now I have to remember in the video, I think it's 1 in 1,000, or was it 4 in 1,000? Somebody can confirm that for me. You know what? I'm not going to put the exact figure, but I think that's what it is. But because I did these calculations before. But what I'm going to say, the most important thing is that so we will be able to see enough deaths and the difference between treatment, this stands for treatment, and control group in a shorter time period than if we used the general, males and females, the population. So that's it. Also, like I say, they're in greater need for help with this, or at the time, this was the 80s. This was conducted through the 80s. And why physicians? So some suggested physicians will have, the main thing about physician is that they're similar. That's the main thing. Physician, I'm just going to say the terms. Similar They are similar in risk factors for heart attack. And we're talking about fatal heart attack, because we're looking for deaths. So I would say they're more similar than other professions. But why physicians in particular? I think we'd have to add, this is a longitudinal study that was conducted over 10 years. And losing people can bias your results, right? If you lose people in a random way, it won't. But if you lose people because they disappear because they actually died, then it's going to confound your results. So it's important to be able to trace your patient's population, and who's better to trace than licensed physicians. So those two are the main reasons. Any other comments about that? So let's see. We have 21,996 physicians prepared to participate in this study. So behind the scenes, we need to randomly assign them to the treatment groups. So how would we label the physicians? What would be the first label? So I have Dr. Bob, Dr. J, Dr. Cow. So I have all these doctors, 21,996. What's my first label? But Liliana, it's okay. It's okay because we're going to randomize them. So we're going to be able to control against that. It can cause a problem. Anyway, it could cause a problem, and we'll talk about that. We'll talk about your comment in a bit, okay? How do I label these doctors? How did you learn in the video to label subjects? We have to think about the last one. What will be the last label? What will be the last label? Start with the last one. The last label should be 21996. So that means the first one should be 00001. The second one should be 00002. And the third one 00003. Get it? So now, we introduce a random digits generator, and let's say the results of the random digit generator are as follows. The first number selected is 00123. So we go down to find the doctor, and we put him over here. So 0, 0, 1, 2, 3 goes here. And the next result in our random digits generator was 0, 1, 6, 6, 5. And so we can put 0, 1, 6, 6, 5 over here. And the next one is 1, 8, 5, 0, 0. Okay, so you get the idea. So I randomize 1, 8, 5, 0, 0. So I randomize them to the different treatments. In such a way. So how many will end up in each group approximately? No comments? How many would end up in each group, approximately? About 5,000, right? Something over 5,000 each. Or 5,500, okay, I can use that number. Okay, so 5,500 each in each group. And then over the course of 10 years, they come and they pick up their prescription every month, or it gets shipped to them, and they have to take it. Now, they don't know which group they're in, but they've been administered different treatment or placebo depending on which group they fell in. After the study ends, or intermittently through the study, as the reports come in about deaths, they start seeing a discrepancy between the people that died in the, let's look at aspirin first, in the treatment group versus the control group. So we're going to be comparing about 11,000 patients in the treatment and the control groups and looking at deaths. And it turns out that over the time that passed, 239 people in the placebo group died for aspirin of heart attacks, and 139 in the aspirin group died. So this was enough to stop the study and say that aspirin is preventative against heart attack. So that way the placebo group people could know that that they were given the placebo so that the study will be broken, and they could start taking aspirin if they wanted to. All right. Similarly, the results for deaths due to cancer were compared between the placebo and the control group, so 11,000 going this way, and there was no significant evidence to support the claim that beta-carotene reduces the incidence of death by cancer. So maybe, you know, the study wasn't long enough to show the effect of beta carotene, or maybe there was some other reason for that, but whatever the case, that was the result of the physician health study back in the 70s and 80s. Any questions? So for the elements of the study, the experimental unit was the individual study participant, which were male physicians. The treatment were the 4 treatments possible, as seen in the chart below. 2 pills taken as a prevention. The response was the death or cause of death. The factors were 2, aspirin and beta carotene. There were 2 levels for each, where I referred to one of the levels being the actual tablet and the second level being the placebo. And that's it. So what we count on is through the randomization process, with 5,500 physicians in each group, we hope the groups have, on a variety of variables, the variation of age, dietary habits, genetic factors that might influence heart attack, and income and education are similar as groups in each of the 4. So we have enough patients in each that we can now compare. When we compare the results of groups, the only difference between placebo and control is actually the treatment. And so any differences resulting from the treatment could be attributable to the treatment. So we say the aspirin has a significant effect, or there's significant evidence to support aspirin prevents heart attack. You know what? I don't know the details about what happened with the beta carotene and the aspirin, but I think they had to stop the study, and I don't know exactly. I'd have to look into it. Do you want me to look into it? But yeah, it could be that they let it go on. I think they had to stop the study, but I don't know for sure. I'm storytelling at this point with that. Whether they could stop it without releasing the information of beta carotene, I guess. I mean, that's not so hard to do now. I kind of think they would have had to stop it because they have to rule out the effect of beta carotene. They had to be able to say that there was no differences in the beta carotene, so that then they could say that didn't influence the aspirin results, something like that. That's my intuition. And maybe I looked at this in the past and that's why I make that statement, but I'd have to double check. But I'm sure there would be questions about the influence of beta carotene, and they'd have to be ruled out. Good questions, though. All right, so let's take a break. We're almost at the halfway mark. Let's take a break, and during that break, I want you to look at example number 4. Well, I'm calling it example, but it should be experiment 4, I guess. Read what's here. You can read. You can read what's here. I want you to try example 4. I have the answers because I'm looking at the annotated results, but let's see if I can hide the answers. Okay, so let's take a 5-minute break. I know how to do this. I'm going to do it like okay, so take 5 minutes and I'll meet you back here. Okay, I'm back. So here's an experiment. And I ask you some questions about it. So this is a food scientist planning to conduct an experiment to investigate the effects of different redox agents, types of flour, and dough mixing methods on quality of loaves of baked bread. There happen to be 3 agents, 3 types of flour, and 2 mixing methods. And these need to be combined, and then bread will be assigned a score for its flavor, loaf volume, loaf density, and crumb texture. What are the factors, the treatments, and the response variables for this experiment? Can you tell me? Okay, so very good. So factors are going to be these mentioned. Redox agents, that's 1. Types of flour, 2. And mixing methods, 3. So those are the factors. And each of them has a different number. There are 3 redox agents, 3 types of flour, and 2 mixing methods. So there's 3 factors. There are how many treatments. So I've mentioned here how you determine the number of treatments, and you can think about the example of the physician health study where we had 2 factors with 2 levels, and that made 4. So what happened? 4 treatments. So it's what you're doing is you're multiplying, right? Like a matrix, number of levels of factor 1 times a number of levels of factor 2. If there are more than 2 factors, you keep going until the number of levels of factor k. So you work with a matrix and several dimensions to find out how many factors you have. So we have 3 agents, 3 flours, and 2 mixing methods, which makes 18. And then response variables are these 4 mentioned here. All right, so what I want you to do next is demonstrate how it is that I have 18. What would the matrix look like? I'll give you a few minutes for that. Let me know when you've done it or if you just can't figure it out. That's right, Gerardo and Jefferson. Okay, so I'm going to suggest we put redox agents over here. And then types of flour up here. And we're going to do this for mixing method 1. So for mixing method 1, we're going to have 9. Then we just repeat. I'm going to cheat. Oops. Yeah, I'm going to cheat. And do the same thing here. As here. But I'm going to do it for mixing method 2. And 9 plus 9 is 18. Got it? So that's what it would look like visually. So we can keep a record of this information. I've taken advantage of control, right? I've controlled the factors that I believe influence the outcome of those response variables. And then I'm going to note I do not need a control group here, right? Why do I not need a control group? I have controlled by controlling the factors and making sure all the different types of bread have a combination of the levels of the factors. But I don't have a control group where they receive no treatment. They're all treatment groups. No idea? It's only with human subjects that I have to create a control group that is a placebo control group, because they might change their behavior. If it's like the Hawthorne effect, they change their behavior, or because of their beliefs, they may influence the outcome. That's the placebo effect. All right, so the last thing to say is how many loaves of flour should I make in each treatment group? Should I make one or should I make many? How many should I make? If I believe there's other variables that I can't control, some variation in the oven or in the ambient temperature or in the yeast that I used, might vary depending on the time of day. If there's other variables I'm not going to control or I can't control, then I should have a few loaves, of each type to avoid, the results just being by chance. So to control against other lurking variables, confounding my results. Okay, no comments? So the second feature required for experiments, the second R is randomization. And we've already talked about randomization. So random means that no one subject has a greater chance of being allocated to one treatment versus another. All right, so this is a different concept than the control concept. We work with them together, right? So example, for completely randomized experimental design, we would need to ensure that all experimental units are allocated at random among all the treatments. So example that I've given you is that you have these volunteers that suffer from migraine headaches being involved in an experiment, and we need to choose the treatment group. So using the random digits table I give you below, how do we do that? Try that again. So I label them. The last one will be the 8th. So I only need to use a label length of 1 because they all have to have the same length. And then working through the random digits table, right, Manuel, we go from digit, so we go one at a time, and 0's not there, so we skip it, and we pick 5, so we pick 5, and then we continue. So 9's not there, 0's not there, skip them, and we arrive at 7, so then we pick 7. And 5 was already chosen, so we skip it. And 0's not there, so then 4 is the next one. And then 9's not there, 5 is already chosen, and then finally 1. So we are not replacing the candidate into the pool, right? We're keeping them out because of the experiment that we're conducting. Once they're in the experiment, I mean, we don't want to use them twice. We're going to use different candidates, which is just fine. And so those are my volunteers that go in the treatment group: Castro Munoz, Rodriguez, and Tulane. Okay, this is my experiment 4. So what I've outlined here is another example for randomization of an experiment. So to illustrate randomization, in this experiment, we've enrolled households who are interested, or they're volunteers, to participate in this study to test which method is better at reducing or conserving energy. So we get a number of volunteers, we recruit 60 households, and then we label them. Since the last one is 60, the labels have to be by 2, so I start with 01, 02, all the way to 60, and then randomly pick from those. The first 20 I pick will go into group 1, the next 20 will go into group 2, and the third 20 will go into group 3, and as I explained, we're going to use all of them. The first group will get this treatment 1, which is they'll be interviewed, or they'll be introduced to the study and told that their meter will be randomly monitored. Somebody will visit and check their electricity meter. They will announce themselves within 24 hours and then show up to read the meter, and this will be done in a random way. The second group will go through an introduction and be shown how to chart their own usage by reading the meter, and they will be visited randomly to check up on them on how they're using the chart. And then there'll be a control group that will be introduced to the study, and they'll be told that they'll be contacted at a later date. Their meter will be read on the first visit. So all of these will have a visit with the research team, representatives, and they will have their meter read, and they'll be told how they will be involved in the study. They won't know about who's also involved in the study. They won't communicate with each other, and otherwise they feel that they're part of a study, but they don't know which treatment arm they are in, because they haven't communicated with the other study. So in this way, this is blinded. I guess the individuals that come to their homes would probably just know about their treatment arm and not know about the others. It could be kept secret. And to make it more double blind. And then at the end of the study, when it's final, that the energy consumption will be compared between the groups. So this is an example of a completely randomized experiment with human subjects with a control group. Any questions? Okay, so finally, the third R is replication. And I mentioned you see there's 20 in each. Determining how many in each group is a a matter for statisticians to sort out based on what they believe, what they believe about the variation, in this case, of energy consumption. But in general, the idea of replication is to have just larger groups, right? So you're going to end up with groups that, to avoid other variables confounding your results, making the groups as groups similar as possible based on those variables, that will mean that you need enough, replications within the treatment groups and the different treatment groups and the control group. Okay, so that you can better establish systematic differences attributable to the treatments. So you can be saying that it's the treatments that are influencing, not the fact that all the people in treatment 1 are very conscientious about conserving energy because they live in a poorer neighborhood or something like that. Okay, so you want to rule out other variables, and so you need enough people to prevent that, or you've controlled for those other factors in some way by your choice of households. So, replication, that you need enough in each of the groups. All right, so some cautions about experimentation motivated by this example. Okay, so let's say you're going to conduct research on a treatment for cancer in human tissue. You're going to use animals, you're going to use rats, and you go out to a field and you try and catch rats for your study. So you go out, you go into the areas, remote areas of the mountains, and you look for rats. What's wrong with doing that? What is a possible lurking variable in doing that? And I suggest, well, the rats that you're catching are possibly older and they can't get away. They might be sicker. And the problem with that is that if you're studying the effect of cancer and you plan to impose cancer-causing agents on them, they might not survive. And so it will bias downward your results, making it look like the treatments that you try to use to make them survive, the imposition of, they put cancer and you've given them some treatment, or you've subjected them to radiation or something, and then you've given them some treatment. The likelihood that they'll survive is much lower. So that's why I say downward bias. So the lurking variable there is the health status of the rats. You're catching the weaker or the sicker ones. And its effect would be to downward bias the results. In conducting experiments, in addition to controlling against confounding effects and lurking variables through using the 3 R's, representation, randomization, and replication, you also want to make sure that your study translates for the general population, or to some general population, relying on the experimental conditions to be meaningful in a general or a different setting would have to be established. You can't just take things that are in a sterile environment like a pilot project or a small-scale biology study on crops and then using the results to say, well, that'll be the same in the general environment, when we know in the environment there are a number of elements that, a small-scale project with crops in a lab or in a greenhouse will not be able to carry to the natural environment. So you want to make sure it's as realistic as possible. You might have to do things in phases to make it as realistic as possible, because you don't want to subject the general population to whatever it is that you're experimenting with, right? So if it's some sort of developed, some fertilizer you're developing, you want to first test it in a pilot study in a small scale in a lab, and then you want to make sure it's safe and do all of those things in a safe environment. And then, once you've determined the safety, then you can go into the broader environment and see how the fertilizer works with the elements, the water, the precipitation, right? With flooding, with the wind, with the sun, and all these other elements, and the air, sun, and water. Those are the elements you have to be concerned with. Okay. Okay, so after all said and done, watching the video, you saw that the importance of observation study to inform experiments, that experiments are actually done. Yet, in the case of the Surgeon General concluding that smoking causes cancer, there was no actual experiment with humans conducted. So what made it possible for him, or the office of the Surgeon General, to be able to say that smoking causes cancer without an experiment? Well, they based it on 6,000 studies over 40 years that were international studies, different locations, different populations, including prospective and retrospective studies, longitudinal studies, including experiments on animal tissue, all showing the same strong correlation between cigarette smoke and lung cancer causing death. And with that, it was considered sufficient to make such a statement. All right? So, do you have any comments? The diligence was required because they were fighting a very powerful tobacco industry at the time. And so they needed this kind of evidence. Now, let's say right now, we are going through this global pandemic where we've been informed that SARS-CoV-2 causes COVID-19. But in fact, this has never been tested in an experiment where people have been infected with SARS-CoV-2 to see if it causes COVID-19 with a control group and all of that, right? But it's been deemed an emergency, and we've taken maximum precaution. But in fact, this has never been proven in an experiment. We do. So my point is that although experimentation is the gold standard, we defer to other methods to avoid unnecessary death, right? Inflicting harm on people. I don't know why this thing crashes. I can only imagine that my files are just huge, but I've checked that. It's not an issue. I don't know. All right. So we are, unless you have a question, looks like we're going to use the whole class to discuss this. Yes, Gerardo. The sufficient number for replications has to be predetermined in a systematic way. So they'd use, the statisticians involved in the experiment would use some numbers, maybe from other experiments people have done, or some convention, and they'd come up with that figure that would be adequate. And it would depend on the variation of energy consumption in households in different areas, something like that. All right, so we're going to talk about sample size. We're going to talk about sample size towards the end of the course, and that's really important, but we're going to do it in a very general or simple way. You know, the whole industry of sampling itself is a specialization. So yeah, so I'm going to teach you some of the basics about sampling and sample size determination. Okay, so we've talked about completely randomized designs, but there are other kinds of experimental designs that are reserved for specific situations. One is the matched pairs design. A matched pairs design compares just two treatments. And this is conducted in such a way where the pairs are chosen, the pairs of subjects are chosen to be closely matched as possible. One will receive one treatment and the other will receive the other treatment. Okay, so we use pairs of individuals if it's human subjects, or in the case of, let's say, plots of land in agriculture, we choose two plots that are side by side or exposed to the same elements. Okay, so we choose them in a way that they're exposed to the factors that could influence the response. And then we study them. One gets one treatment, one gets the other. So we control in this way for lurking variables or other variables. So the classic example for matched pairs in human subjects is to use twins. So identical twins in particular, identical twins who have all the same genetic makeup, when we study one treatment on one and a treatment on the other, provided they were raised in the same environment, we can actually see the different effects of the treatment, right? So twins are very popular in research. Also, twins that were separated at birth are very interesting to study. So, so you can look at the difference that environmental effects can have, or the impact the environmental conditions can have relative to genetic characteristics. So you have identical twins separated at birth, so now you can see what characteristics of the individuals is attributable to their genes. And some of these studies, you can see these on shows or programs, or what are they called, stations, channels, like, I don't know if they still have TLC. They do these kind of reports on twins, and they show that twins separated at birth, they'll be found to be married to a woman, like, men then separated at birth will be married to a woman named Pat, and they'll both be engineers. So it's very interesting because that would imply that those are genetic predispositions and not because of their environmental experience or exposure, that their upbringing or their, the school they went to influenced their decisions. It's actually programmed that they would marry a woman by a certain name. It's very interesting. The problem with twin studies alone, though, is that there's not a lot of twins separated at birth that they've found to study, and so some of those could just be coincidence. They'd need, a substantial number of twins, and they're working on it. There are people very interested in identifying genetic characteristics, genetic traits that influence our preferences. Okay, so the classic type of twin, like the twin study I mentioned, for matched pairs exists. And then there's one that's more popular since the 70s and 80s. There was the Pepsi challenge. The Pepsi challenge is an example of a matched pairs study. Now, if you're familiar with it, this is where individuals either in an amusement park or somewhere where there's a crowd, maybe at the front of a concert or something, there'll be a kiosk set up inviting individuals to take the Pepsi challenge, and the individual will be presented with, if they agree, right, they're presented with a can of cola, and they drink the cola, and then they're asked to just wait a bit, and then they drink a second can of cola, and they determine which one they preferred. How can you make this, where one of them is Coke and one of them is Pepsi, and then because it's the Pepsi challenge, it always turns out that they like Pepsi better. So that's how it's demonstrated on in commercials. And I have nothing to say about the truth or falsehood of that, just that that's the commercial. So how would we make this an actual experiment? How would we ensure this was actually an experiment that used the 3 R's: representation, randomization, and replication? So describe to me what would be the control or representation. How is randomization used? And how is replication visible? How do we identify replication? Okay, the easiest one to start with is a replication, right? The replication is just many individuals showing up at the kiosk. The control, remember, what is it? Match pairs. You choose pairs of subjects that are closely matched as possible. Well, what better match than the person themselves? So you're using one person to receive both treatments. You see how the matching is with the idea of the match is that they're as close as possible, and then one person of the pair gets one treatment and the other person of the pair gets the other treatment. Well, we're going to make the person themselves the control, and they're going to be the control subject because they are going to receive both treatments. Because they are the same, right? From drinking one can to drinking the other, the person didn't change. It's an identical person, except that they had the other can. So we have to do something to make sure, to ensure that the order of which the cans were tasted, or the contents of the cans were sampled or tasted, does not affect the response. So we're going to randomize. So what happens is the cans are previously sorted and marked as 1 and 2, like which one goes first and second, and it's done in such a way that the order through flipping a coin between Pepsi and Coke going first is randomized. So if it's done this way, the Pepsi versus Coke taste, or the Pepsi challenge, would be an experiment. Any questions? No questions? Okay, so the control is the individual themselves. The randomization is the order of the cola drinks. And the replication is just many people. Is that a summary? So the control is the individual who gets both treatments. The randomization is the order of drinking the cans that has been randomized previously. And the replication is the number of people. Many people being asked to take the Pepsi challenge. I hope that's okay. So you guys can watch the video again, all right? So my My grade, sorry, the TA will be putting the timestamps on the video, so you can come back to this this spot on the video and review what I said. All right, so a matched pairs design is an example of a block design. The blocks in a design receive all of the treatments, just like the individual gets both Coke and Pepsi to try. So we create a block, or we identify a block, we separate the subjects into blocks, and otherwise we don't randomize all of the subjects. First we separate them to blocks, and then within the blocks the randomization takes place. So why is that happening? Why do we do that? So here's below is an experiment. So this is an experiment to test the effect of a new treatment on cancer. Now let's say we invited, through referral by doctors, the patients were invited to participate in this study. And let's say we waited, we identified, we needed about 90 patients to participate to be able to attribute effect. So that would be enough to be able to say if there was an effect, we'd be able to find it. So let's say we label everybody. So I said 900, right? What did I say? 90? Yeah, I said 90, sorry. So 90 is the last person. So we'd have to label everybody up to 01. Okay, 01 to 90, you label all your candidates, and then you randomize them into the groups. So there would be 30 subjects in group 1, 30 subjects in group 2, and 30 subjects in group 3. Group 1 would receive therapy 1, so this would be the new treatment that's available. We're going to compare it to treatment 2, which is the old treatment, and then we need a control group. So let's say this was our study, and then we compare the survival of people with the 3 different treatments. What's the problem with this? Well, in advance, we're aware that this new treatment I write it here. So we're going to compare cancer treatments that are known to affect hormone levels. So treatment 1 and treatment 2 are known to affect the hormone levels. So men and women respond differently. So sex hormone levels. So we know that by conducting the study in the way that I've proposed, we risk the possibility that only men are assigned to group 1. And then maybe only women are assigned to group. It could happen. It could happen. that only men or mostly men in group 1, mostly women in group 2. And then this will confound the effects of the treatment because maybe any differences that are found in survival are attributable to the gender of the person and not the treatment. Because we know that there is an effect that's different for men and women. So to avoid this problem and a potential confounding, we block. We separate women and men differently. We separate them into blocks. Now notice the study looks the same, right? The randomized controlled study looks the same, except these will all be men, and these will all be women. And they'll receive all 3 treatments: the new, the old, and the control. Now, I might not have an equal number of men and women, but I could still use the 90. There's a tendency for more women usually to enroll in studies. That's maybe because they're not the breadwinner of a family, they're not working, and they're available. But it's just that way. So whatever the case is, I'm going to split the men and women and then conduct the study. Sorry. Any questions? I've written what I've said around here, so you can read that after and watch the video again. So the blocks, the important takeaway is that the blocks receive all treatments. In this way, I don't need to have more subjects involved in my study. I avoid confounding possibility where, this happens, mostly men in one and mostly women in the other group. But because I've made my the variation among the groups similar as possible, I don't have to add any more subjects. If this was the situation, if I was faced with this situation after setting up the study, I would have to postpone the study until I had more subjects. Okay? And that every subject adds a cost, right? You have to collect data. There has to be an interview. They have to be assigned to a nurse. They have to be assigned the drugs. So every candidate, every subject adds an incremental cost. All right. So question, how does a block design differ from a completely randomized design? Is there more information supplied? The difference is that the randomization occurs within the blocks. Okay, so first we block by nature, there's men and women, they split into 2. And then the more restrictions there are, the more information will be supplied. Okay, so we're teasing apart characteristics that can confound our findings, and we group people into more similar in their response to a treatment than if you were allowing the 2 genders to be randomized to treatments. So the primary reason for using a matched pairs design or block design rather than a completely randomized design is that more precise conclusions about the treatments can be attained for the same cost. This is the point that I made toward the end. The idea of block in experimental design is comparable to the stratum in sampling design. So if you remember in the video, you learned about strata, or stratification. Okay, stratification in sampling is like blocking in experiments. The idea being to get adequate representation. Okay. Okay. So let's take some time now. I've looked at experiments. You can read through these and convince yourself that A is the best answer. But otherwise, I'm going to move on to the discussion on sampling. Yeah, I see, I can't, don't know why I can't stick it together. Oh, anyway, let's just erase that. All right. So for the terminology, a population is the complete set of all items that interest an investigator. Population size, capital N, can be very large or infinite. We talked about this first class. A parameter is a numerical measure computed from the value of a variable on all items of the population that describes that specific characteristic. A sample, on the other hand, is an observed subset or portion of a population with sample size given by small n, and a statistic is a numerical measure computed from the value of a variable on all items of the sample that describes that specific characteristic of the sample. So we discussed this last class, and I discussed remembering that a parameter, I think I did, is computed from a population, and a statistic is computed from a sample. So if it helps at all, P with P and S with S, okay, for the terminology. So I'm going to be very precise about that terminology. So this is just a repeat of what I said, and I gave an example here for some of the symbols used that we'll talk about, I guess, next class. So the proportion of people who are employed in a country, known as the population proportion, symbol P, is estimated that by the sample proportion P hat. So here are some of the statistics that we're going to talk about in this class. X bar is the sample mean, S is the sample standard deviation, and P hat is the sample proportion. These are estimates of the parameters mu as the population mean, sigma as the population standard deviation, and p as the population proportion. So those you'll understand and how to calculate all those soon enough. So this is just a review of the video. If you remember in the video, the discussion about the trucks with the potato chips and identifying, the elements of the sample. The population would be the 45,000 pounds of potatoes in the truck. The units would be the potatoes in the truck. The sample would be taken from remember the 5 buckets that contained about 30 pounds each of potatoes, and the units would be the potatoes in those 5 buckets. So that's just some of the terminology for sampling. We want to be sure to avoid bias in collecting a sample. We don't want to just use, you don't want to repeatedly pick subjects or but the units that we prefer. So I provide the example of Briex, where they were mining for steel or minerals that this company was an extracting company. It was an exploration, an extraction company, and they were caught fraudulently reporting pieces of from their mine that contained the substance they were looking for. Anyway, you can look up Briex and the scandal of Briex in the 90s if you're interested. You want selection to be random. You don't want people choosing themselves. You don't want self-selection. So I described the hormone replacement therapy in the sample of people reporting good outcomes in observational studies, and that wasn't sufficient. An experiment revealed that those people were self-selecting themselves into getting hormone replacement therapy, and it turned out that they were different than the general population. So the conclusion was that you couldn't attribute those outcomes to the general population. So you got to be careful of bias, people opting in to answer questions and their own personal bias in responding. Here's another example of sampling, randomization. In sampling, and what the takeaway of this exercise is, if you do it, I label, because there's 8, I use labels of length 1 because labels have to be the same length, and I begin choosing, and if I label them 1 through 8, I get the answer B. But I'm not given instruction on how to label. So without instructions on how to label, I could have gotten a different sample. What if I labeled them like this? This is not wrong. As long as the labels are equal length, I will, however, get a different result, right? The answer turns out to be C, which is different from B. So also, if I label them starting with 0, which is also permissible, I label them with 0 through 7, I get a different answer still. I get answer D. So these are all correct, so the best answer is E. In a test situation, I won't I won't expect you to do that unless I'm a little more explicit about the possible answer. The fact is, without giving you instructions on how to label, label the first person in the list with a 1, without that kind of instruction, all of these are acceptable answers. So try that out. And then I mention here, there's a discussion about sampling with and without replacement, and the fact that whether you're choosing with labels of size 1 or labels of size 2, this continues to be a simple random sample, because each outcome has equal chance of being selected. So read through that. And let me know if you have any questions. The general framework for designs is that they use chance to choose a sample. A probability sample is a sample chosen by chance, where we know what samples are possible and what chance or probability each possible sample has. The simple random sample is even stricter, requiring that each member of the population has equal chance of being selected. So a simple random sample has those two requirements, or I say requirements, but consequences or implications. For a simple random sample, each sample of size n has equal chance of being selected. But also, each member of the population has an equal chance. Okay, a probability sample only has this feature. So this is all in regards to the sample. All right, so think about that. And now I want to talk about the difference between stratified and what's called multi-stage samples. Yes, Gerardo. You can label them as long as you label, the labels are of equal size. It doesn't matter how your list first appears. All right. So, as explained regarding block design for experiments, I said that stratified design is similar for samples. We use stratified sampling when we know in advance that individuals or households or subjects, we'll know that our units of interest vary in particular ways. And we would have to select a larger sample to be able to have meaningful results. To avoid that additional cost, we pre-stratify. Okay, we pre-stratify. We separate. For instance, in the video that you watched, there was a discussion about wanting to have a representation of urban, suburban, and rural households. And the risk is that if you label households in a region, so you start labeling them, and you just do it, like go ahead and start labeling everyone you have on a list of taxpayers, say household property taxpayers or something like that, to get a list, and you start labeling them, and then sampling from them. Because there's so few people living in the rural community, you might not get anyone represented from the rural community. So to avoid that, we stratify. So urban, get a list for each. And then get a simple random sample from each. This way you avoid missing representation of rural households. And biasing your findings. I'm hoping my writing isn't messy, but the fact that I look back and I don't know what it says is an indication that it's messy. So let's see like that. Stratified sampling is different from multi-stage sampling. However, they're used together often in census, where you want to do this and have representation, but you run into another issue that your lists are so big and hard to update, costly and time consuming, which is also costly, to keep up to date, that you need another technique to help you along, and that's what multi-stage is for. So when lists are huge, this addresses the problem. So if you want to randomize households, you need an accurate list that's up to date with full information to be able to contact these people. People change their numbers, people move. It's hard to know if your list is up to date, and it's doubtful. So imagine if you had 18 million households to sample from. Here I want to study, in this example, I want to study consumption of whole foods, and I want to study in a region of 18 million households. But I only have money to survey 12,000. So how do I reconcile this, and how do I choose? Do I just choose from the households I have information from? Well, that's not random, right? We need to approach this in a random way. So this is the idea where we introduce multi-stage. We focus slowly in, so we imagine like a lens, right, of a camera, and we pull out as much as possible, and then slowly, step by step, stage by stage, zero in on our candidates, on our units. So, for example, let's say we begin with the regions in a territory, or in a broader country. I mentioned country. So we label all the regions because, well, it's easy to get a list of regions, right? In Puerto Rico, there's 78 municipalities, I think. So those, you could use those as regions. And let's say there were 30. Okay, so in this country, there are 30 regions. And what I'm going to do is just label those. So I will label those 0, 1, 0, 2, all the way to 3, 0. Now, let's say you believe that the regions were distinctly different in reference to how they eat, and you had some idea in advance how to stratify, and you can do that too. So you could stratify them, and then within the strata, conduct a multi-stage sample. That's what you could do. So, so from these 30, I've been told that a third is enough. So the statistician expert in sampling indicates that sampling 1/3 from the 30 is good enough. So we began selecting from the 30. We get, well, what's a third of 30 is 10, right? So I pick 10 from here using a random digits generator. Okay, so now I've got 10 regions. Now in those 10 regions, so what I'm doing is I'm narrowing, or I'm focusing only on a smaller group, not all 18 million at a time. So from the 10 regions, I identify there's about 30 communities in each. And I've been told that of the communities, you only need to sample 20%. So I see that it's 10:02, so we are going late. I'm going to finish this. If you have to go somewhere, go ahead and check back on the video to see how I finish this off. But I'm just going to finish talking about multi-stage, and then I will say that I am done with Unit 1. You're going to have to read through the rest and ask me questions if you're stuck. But Unit 1 is going to be done for today, and we're going to start Unit 2, GDS, next class. So let me finish this. I'll say goodbye to those who need to go. Okay. So as I was saying, stage 2. Stage 2 is 30 communities, and we sample 20% from each region. So we label them in each region. 0, 1, 0, 2, 0, 3, 0, 4, well, I'm going too far, up to 30. And we randomly select from them. And 20% of 30 is 6. So I'm going to pick 6 in each region. So that's a total of 60 communities. So now I have 60 communities from stage 2. From stage 2, I move in and I see blocks. So there's 200 blocks, let's say. It could vary, but let's say there's 200 in each community. So, and I think 2% is a good enough sample. So 200 in each community, I start to labeling, so 0, 0, 1, 0, 0, 2, all the way to 200. Right? And I have to choose 2%, which is 4. So I'm going to choose just 4 from 200 randomly, but I'm going to do it for all 60 communities. So 60 times 4 is 240 blocks. Finally, we arrive at the households. The household level, now in the blocks, there are about 100 households on each block, so I will label them 0, 0, 1, 0, 0, 2, all the way to 100, and select from here for each of the blocks, 240 blocks, I'm going to pick 5%. So it's going to be 5 total from each times 240, which is 1,200. So this is a multi-stage sample design, and we do this because of an issue with the lists, and just that it's hard and costly with little benefit it's very wasteful to try and get an up-to-date list of 18 million households. When you start assigning, so if you randomly selected from the 18 million, you might find that people just don't respond because you got the wrong address or you got the wrong people at the address. Okay? So this makes it less likely that you have bias in your study, missing people who are transient. So there's the advantage. The disadvantage of this is just obviously someone has to be hired to come up with all these numbers and then help us compile everything together after the sampling is done. So this can be costly, but in these large studies, these government studies, they have the resources and they've appropriated funds to do this kind of research. All right, so I'm going to stop there, like I said. All you have to do is read through this. I'll mention a few things when we start next week, but you're ready to go ahead and solve these quizzes in there and the quizzes online and try these practice assignments. All right? Any questions? So I just wanted to see, let's see in the prontuario, the syllabus, I want to make sure we're on a good schedule. Did I erase it? I did. I did erase it. Let's see if I put it here. No, I'll have to see, but I'll make it work. The first test, I think, if somebody can tell me, was it February? No, Liliana, you don't have to turn in anything. You need to study those on your own, all right? That we're just going to have a test. I'm looking for the date. I'm going to see on... on my super long prontuario. I know it's in February, I just want to be sure. Oh yeah, we're good. By February 20th, we will finish GDS. So the first test will be on GDS and NOR. And Unit 1. So Unit 1 and Unit 2 should be done. I'm going to double check on Moodle. I'm just checking, verifying the first test. So the online quizzes are for you to complete. You have as many attempts as you like. And one of those will go towards your final grade. I'm just confirming that it's consistent throughout. And I mentioned in the layout, yeah, units 1 and 2 for the first test. So we'll be done by February 20th for sure. Okay, so make sure you have your calculator for next week, and let me know if you have any questions. Have a good weekend, and review everything, and don't let it build up, all right? Make sure you do the work. I'm not there to monitor you. It's up to you. But I'm here if you have any questions. And just in time before construction starts, I'm going to sign off. I'll look on the chat for a bit. I'll just turn my microphone off, and let me know if you have any questions.